Thank you for joining another math lesson hosted by Book and Table. I am your math tutor, Maurice Wright, and in this chapter we are going to review Cramer's rule. We'll review how to find the determinant of both 2x2 and 3x3 systems, and we'll also review how to use Cramer's rule to solve both 2x2 and 3x3 systems. Should you have any follow-up questions, feel free to leave them in the comments section, or you can contact a tutor in your neighborhood by visiting bookandtable.com or by downloading our app on the App Store. So let's begin by discussing 2x2 systems. A 2x2 system has two equations with two unknown variables. The substitution and elimination methods can be used to solve a system. So this here would be an example of a 2x2 system. Our first equation is x minus 2y is equal to negative 7. And our second equation is 2x plus 3y is equal to 7. So we see in both equations we have two unknown variables, our x and y. So in our 2x2 systems chapter, we reviewed the substitution and elimination methods for finding the value of x and y in this system. In this chapter, we'll be using a process known as Cramer's rule to find x and y for a 2x2 and a 3x3 system. In order to do so, we must first review what a matrix is, specifically a coefficient matrix. A coefficient of a term is the number in front of the variable, and a matrix is a grid of numbers. A coefficient matrix is a matrix of the coefficients from the system. So here, our coefficients in this row here in this equation are 1 and negative 2. So in this matrix here, row 1, we have positive 1 and negative 2. The coefficients in our second equation are positive 2 in front of our x and positive 3 in front of our y. So those go in our coefficient matrix in the second row. And a matrix is denoted with brackets on both sides of the grid of numbers. So this would be an example of a coefficient matrix. We have a grid of numbers that represent the coefficients from the equations. Now, the determinant is a number that can be calculated from the coefficient matrix of the system and is denoted by two vertical lines. So throughout this chapter, instead of two brackets on the two sides of our grid of numbers, we'll have two straight lines such as these two here. And this is what we'll be using to show that we're calculating the determinant of this matrix. Now let's review some basics about a matrix, just so we're clear about the language that I'll be using throughout this chapter. Rows are represented by the letter R, are aligned horizontally, and are counted from top to bottom. So we start with row 1 at the top of our grid. As we make our way down, the next row is row 2. And as I stated, they go horizontally. So it's moving from left to right. Columns are denoted by the lowercase c and are aligned vertically and are counted from left to right. So we start all the way to the left on our grid. This is the first column, C1. This is the second column, C2. So 1 is in row 1, column 1. So this spot in our grid here can be represented with the expression R1C1, the first row, the first column. Positive 2 beneath it. We are now moving from row 1 to row 2. So we have row 2, but we're in the same column, so that's column 1. So this spot in our grid can be represented by R2C1. Negative 2 here, we're back in the first row, so this is R1. But now we've moved from column 1 to column 2. So this spot in our grid can be represented with R1C2. And positive 3 is in the second row in the second column, so it can be represented by R2C2. This will help make the steps that we're going to use for calculating a determinant a little bit clearer. Now, Cramer's rule can be used to find the solution, or the xy coordinate, of a 2x2 system and the solution, xyz coordinate, of a 3x3 system. So we'll be using determinants for a 2x2 system, and then from those determinants, we'll calculate the x coordinate and the y coordinate for the solution in a 2x2 system. And then Cramer's rule can also be applied to 3x3 systems as well. And we'll use a set of determinants to calculate the x coordinate, the y coordinate, and the z coordinate of that solution. So we'll wind up talking about each of these things throughout the remainder of this chapter. So let's now move on to discussing 2x2 determinants. The determinant of a 2x2 system can be calculated with the following formula. So the determinant D is equal to, we have our coefficient matrix between our two vertical lines. And the formula is we take the number that is in the first row, column 1, and we multiply it times the number diagonally down to the right here. So we would be multiplying A times D. And then we subtract the product of the number that's in the second row and first column times the number up and to the right, which would be row 1, C2. So we wind up multiplying C times B, giving us AD, multiplying down to the right, minus CB, multiplying up to the right. So let's say we had 1, 2 in the first row and 3, 4 in the second row. We would have 1 times 4 minus 3 times 2. And then using this expression, we can then solve for D for this 2x2 system. Remember, these numbers represent the coefficients of a system, but we're just going to work with the matrix for now to practice solving for the determinant. So let's walk through an example from the start. We have a 2x2 matrix, and we're asked to find the determinant. We have 2, -1 in column 1, and 5, 3 in column 2. So step 1, multiply the numbers going down to the right, starting with R1, C1. The first row is furthest to the top. The first column is furthest to the left. So that would be positive 2 here. And we want to multiply the numbers 2 and 3. So we're going down to the right. So we have 2 times 3. And then the second step is to place a minus sign after the product from step 1. So we have 2 times 3 minus. And now step 3, we want to multiply the numbers going up to the right, starting with R2, C1. So the second row and the first column leads us to -1. And we want to multiply -1 and 5, since we're going up to the right. So we wind up with 2 times 3 minus -1 times 5. So now we can solve for D. 2 times 3 is equal to 6, minus -1 times 5 would be -5. 6 minus -5 is equivalent to 6 plus 5. So we see that D is equal to 6 plus 5, which means the determinant is equal to positive 11. So that is how you would find the determinant of a 2x2 matrix. Let's now have you try a few practice questions. Question number 1, find the determinant of this 2x2 matrix. Column 1, we have positive 1 and -1. Column 2, we have -2 and positive 3. Question number 2, column 1, we have positive 2 and -3. Column 2, we have positive 4 and -2. Question number 3, column 1, we have -1 and positive 3. Column 2, we have -3 and positive 5. And question number 4, column 1 is -3, positive 5. And column 2 is positive 4, -2. Pause the video answer these questions, and then press play when you are ready to begin. Question number 1. Step 1. Multiply the numbers going down to the right, starting with row 1, column 1. So the first row is furthest to the top. The first column is furthest to the left. So row 1, column 1 is positive 1 here. And we want to multiply going down to the right. So you multiply positive 1 times positive 3. Now step 2, we want to place a minus sign after the product from step 1. And now step 3, we want to multiply the numbers going up to the right, starting with R2C1. So that would be negative 1. And if we're multiplying going up to the right, we multiply that times negative 2. So that gives us 1 times 3, which is positive 3, minus negative 1 times negative 2, which would be 2. So we see D is equal to 3 minus 2, which means the determinant for question number 1 is equal to positive 1. Question number 2. Step 1, multiply the numbers going down to the right, starting with row 1, column 1. So that means we're multiplying 2 times negative 2. And then step 2, we want to place a minus sign after the product from step 1. And now step 3, we want to multiply the numbers going up to the right, starting with the second row, column 1. So that would be negative 3. And if we're multiplying going up to the right, that means we're multiplying negative 3 times 4. So now we can solve for D, giving us 2 times negative 2, which is negative 4, minus negative 3 times 4 is negative 12. Negative 4 minus negative 12 is equivalent to negative 4 plus 12, and that would be positive 8. So the answer to question number 2 is the determinant is equal to positive 8. Let's now have a look at question number 3. Step 1, multiply the numbers going down to the right, starting with R1C1. So we multiply negative 1 times 5. And then step 2, we place a minus sign after the product from step 1. Then step 3, we multiply the numbers going up to the right, starting with R2C1, which would be positive 3. So if we go up to the right, we see that we want to multiply positive 3 times negative 3 here. And now step 4, we can solve for D. So we have negative 1 times 5, which is negative 5, minus 3 times negative 3 is negative 9. Negative 5 minus negative 9 is equivalent to negative 5 plus 9, and that would be equal to positive 4. So the answer to question number 3 is the determinant is equal to positive 4. So that is the answer to question number 3. Let's now have a look at question number 4. Step 1, multiply the numbers going down to the right, starting with row 1, column 1. So that would be negative 3. And if we're going down to the right, we want to multiply negative 3 times negative 2. And now we want to place a minus sign after the product from step 1. And step 3, we want to multiply the numbers going up to the right, starting with R2C1, second row, first column. So that would be positive 5. Going up to the right means we're multiplying 5 times 4. So now to solve for D, we have negative 3 times negative 2, which is positive 6, minus 5 times 4, which is 20. Showing us the determinant is equal to 6 minus 20, which would be negative 14. So that is the answer to question number 4. And that is how we go about calculating a 2x2 determinant. Let's now discuss how we use this to solve a 2x2 system using Cramer's rule. Cramer's rule is a process that uses three unique determinants, d, dx, and dy, to find the solution, or the xy point, to a 2x2 system. So we have a 2x2 matrix, as we saw in the previous section of this chapter, but now we'll be introducing dx and dy, and these will help us find the exact x and y coordinates of our solution. But before we walk through an example together, let's first discuss dx and dy a little bit further. The determinant dx is calculated by replacing the column with the coefficients of the x variable with the numbers that represent the total value of the equations. So let's say we had ax plus by is equal to e as one equation, and cx plus dy is equal to f as the second equation. A, b, c, and d are the coefficients. So for the determinant of this 2x2 system, you would take a, the coefficient of x, c, this coefficient of x, and that would be the first column. Here we have the coefficient of y, which would be b and d, so those would be placed in the second column. And then we use the formula for a 2x2 determinant to calculate the determinant of this system. But the determinant dx, what we want to do is replace a and c with the total value of each respective equation. So since we're replacing a, we want to replace it with the total value of the same equation, which would be e. So we have e in the first row, first column, instead of a. And we replace c, the coefficient of x, with the total value of the equation, which would be f. So instead of c here, we have f. And now this is the 2x2 that we'll use to calculate dx. We're going to multiply e times d, and then subtract f times b, and this will give us dx. And the third determinant would be dy, and that is calculated by replacing the column with the coefficients of the y variable with the numbers that represent the total value of the equations. So for dy, the column with the coefficients from our x variable are left untouched, so it's the same as the regular determinant. So we have a and c, but when we're calculating dy, we replace the column with the y coefficients with e and f, the total value of each equation. And this is now the 2x2 that we'll use to calculate the determinant dy. So we do a times f minus c times e. So we'll use each of these determinants to help us calculate the solution, x and y. Now the values of the determinants d, dx, and dy can also let us know if the system has no solutions or if the system has an infinite number of solutions. If the determinant of the coefficient matrix is equal to 0 and both the dx and the dy determinants are equal to 0, then the system is dependent and has infinite solutions. So one thing you will have to remember is if you get d is equal to 0 and dx is equal to 0 and dy is equal to 0, that lets you know that the system has an infinite number of solutions. But if the determinant of the coefficient matrix is equal to 0 and either the dx or the dy determinant is not equal to 0, then the system is inconsistent and there are no solutions. So you get the determinant is equal to 0 and either dx or dy is not equal to 0. So if you get dx is equal to 2, or if you get dy is equal to -4, if you get any value that is not 0 for either of these, but you get d is equal to 0, that combination lets you know that that system has no solutions at all. So keep both of these use cases in mind as you begin to calculate the determinants for your system. Let's now walk through an example together. You'll be asked to use Cramer's rule to solve the system and then check the answer. Equation A, x plus 3y is equal to negative 5. Equation B, negative 2x minus y is equal to negative 5. So step 1, we want to take our 2x2 system and create a coefficient matrix. So the first column, the coefficients of our x variables will be positive 1 and negative 2. The second column will be the coefficients of our y terms, which would be positive 3 and negative 1. So the determinant of the system will be equal to this 2x2 system. So now step 2, we can solve for d. So we want to multiply 1 times negative 1 first. And then we place a minus sign after that. And then multiply negative 2 times 3. So now we have 1 times negative 1 minus negative 2 times 3. So when we solve for d, 1 times negative 1 is negative 1 minus negative 2 times 3, which would be negative 6. Negative 1 minus negative 6 is equivalent to negative 1 plus 6. So we see d is equal to negative 1 plus 6, which would be equal to positive 5. So now that we found d, we want to put this information to the side and now try to calculate dx. So step 3, replace the first column of the coefficient matrix. So that would be the coefficients of our x terms with the values of the respective equations. Replace 1 with negative 5, the value of the equation where we find that coefficient. And we want to replace negative 2 with negative 5, the total value of the equation for that coefficient. So this would be the 2x2 that we use to calculate the determinant dx. So now we can do so by multiplying negative 5 times negative 1. And then we subtract the product of negative 5 times 3. So we wind up with dx is equal to negative 5 times negative 1, which would be positive 5, minus negative 5 times 3, which would be negative 15. 5 minus negative 15 is equal to 5 plus 15, and that would be equal to 20. So we see that the determinant dx is equal to positive 20. So you can put this information to the side, and now we want to calculate the last determinant, dy. So we want to replace the second column of the coefficient matrix, the column that has the coefficients of the y term, with the values of the respective equations. So we want to replace 3 and negative 1 with negative 5 and negative 5. In the first column, you can make the coefficients of the x terms again. So the determinant dy is equal to this 2x2. Column 1, we have positive 1, negative 2, the coefficients of our x terms. Column 2, we have negative 5, negative 5, the total value of the equations, not the coefficients of the y term. And now step 6, we can solve for dy by multiplying 1 times negative 5. And then we subtract the product of negative 2 times negative 5. And now we can solve for dy. 1 times negative 5 is negative 5. Minus negative 2 times negative 5 is 10. Negative 5 minus 10 shows us that dy is equal to negative 15. So now that we know d, dx, and dy, d is equal to 5, dx is equal to 20, and dy is equal to negative 15, we can now use these three pieces of information to find x and y. So we first want to divide dx by d so that we can solve for x. So I'll put the equations to the side for a moment since we just need to work with these three determinants for now. And now when we divide dx by d, we get x is equal to 20, this is dx, divided by 5, which is d. and 20 divided by 5 is equal to positive 4. So we see that x is equal to positive 4. But this is only a part of our solution. We now need to find y. So step 9, we want to divide dy, which is negative 15, by d, which is positive 5. This will give us the y-coordinate. So y is equal to negative 15 divided by 5, which is negative 3. So we found the value for x and we found the value for y. X is equal to positive 4 and y is equal to negative 3 is the solution to this 2x2 system. And we can check this answer by plugging the xy, 4, negative 3, into the original equations, a and b. When we plug 4 in for x and negative 3 for y, we get 4 plus 3 times negative 3, which should be negative 9. 4 minus 9 is equal to negative 5. So the first equation is true when we have x is equal to 4 and y is equal to negative 3. So those are the correct values for x and y for the first equation. For equation b, we have negative 2 times 4, which is negative 8, minus negative 3, which is positive 3. Negative 8 plus 3 is negative 5. Negative 5 is equal to negative 5. Confirms that x is equal to 4 and y is equal to 3 for equation b as well, and thus is the solution to this 2x2 system. So that is how you go about using Cramer's rule to solve a 2x2 system. Let's now have you try a few practice questions. Use Cramer's rule to solve the system and then check the answer. Question number 1, equation A, negative x minus 2y is equal to negative 8. Equation B, 3x plus y is equal to negative 1. Question number 2, equation A, negative 2x minus y is equal to 8. And equation B, negative 3x plus 4y is equal to 23. Question number 3, equation A, 2x plus 4y is equal to negative 2. And equation B, negative 3x plus y is equal to negative 11. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1, create a coefficient matrix. So we are given a 2x2 system. So we want to take the coefficients of our x terms, negative 1 and positive 3, and those would be the numbers in the first column. Then we want to take the coefficients of the y terms, negative 2 and positive 1. So those will be the numbers in column 2. And now we can solve for d by multiplying negative 1 times positive 1. And then we subtract the product of 3 times negative 2. So we see d is equal to negative 1 times 1, which would be negative 1, minus 3 times negative 2, which would be negative 6. Negative 1 minus negative 6 is equal to negative 1 plus 6. And that's equal to positive 5. So we see that d is equal to positive 5. We can now put that to the side, and we want to focus on finding dx now. Replace the first column of the coefficient matrix with the values of the respective equations. So for dx, we want to replace negative 1 and 3 with negative 8 and negative 1. And now we can solve for dx. So we first want to multiply negative 8 times 1. And then we want to subtract the product of negative 1 times negative 2. And now we can solve for dx. Negative 8 times 1 is negative 8, minus negative 1 times negative 2, which is 2. Negative 8 minus 2 is equal to negative 10. So we see that dx is equal to negative 10. And now we want to put dx to the side and calculate dy. So step 5, replace the second column of the coefficient matrix with the values of the respective equations. So we put back negative 1 and 3, the coefficients of the x terms, into column 1. And we replace the coefficients of the y terms with negative 8 and negative 1. And now we can solve for dy by multiplying negative 1 times negative 1. And then we want to subtract the product of 3 times negative 8. Now we can solve for dy, giving us negative 1 times negative 1, which is positive 1, minus 3 times negative 8, which is negative 24. 1 minus negative 24 is 1 plus 24. So we see that dy is equal to 25. So now that you have calculated d, dx, and dy, we can now try to find the values of x and y. So we'll start with x. So we want to divide dx, which is negative 10, by d, which is positive 5. So let's put these two equations to the side for a moment and just work with our determinants. When we divide negative 10 by 5, we see that x is equal to negative 2. And now we want to find the y coordinate. So we want to divide dy, which is 25, by d, which is positive 5. So if y is equal to 25 divided by 5, that shows us that y is equal to positive 5. So the solution to this 2x2 system is the point where x is negative 2 and y is positive 5. And now we want to check the answer by plugging the xy, negative 2 and positive 5, into the original equations to make sure both equations are true with these two values. So when we plug in negative 2 for x, we get negative 1 times negative 2, which is 2, minus 2, and we plug in 5 for y. Negative 2 times 5 is negative 10. 2 minus 10 is equal to negative 8. Giving us the true statement, negative 8 is equal to negative 8. So these are the correct values for x and y for equation A. And now equation B, we have 3 times negative 2, which is negative 6. Negative 6 plus 5 is equal to negative 1. Negative 1 is equal to negative 1 is a true statement as well, confirming that this is the correct solution for equation B as well. And thus the answer to question number 1 is the point where x is negative 2 and y is positive 5. So that is the answer to question number 1. Let's now have a look at question number 2. Step 1, create a coefficient matrix. So the first column will be the coefficients of the x terms, which would be negative 2 and negative 3. The second column will be the coefficients of the y terms, negative 1 and positive 4. And now we can solve for d. So we multiply negative 2 times 4. And then we subtract the product of negative 3 times negative 1. So to solve for d, we have negative 2 times 4, which is negative 8, minus negative 3 times negative 1 is positive 3. Negative 8 minus 3 is equal to negative 11. So we see that d is equal to negative 11. So we can put this to the side, and now we want to try to find dx. So we want to replace the first column of the coefficient matrix with the values of the respective equations, 8 and 23. So now we can use this 2x2 to solve for dx. So we want to multiply 8 times 4. and then we subtract 23 times negative 1. So we see dx is equal to 8 times 4, which is 32, minus 23 times negative 1, which is negative 23. 32 minus negative 23 is equivalent to 32 plus 23. And 32 plus 23 shows us that dx is equal to 55. So now we can put dx to the side and focus on finding dy. So to find dy, you want to replace the second column of the coefficient matrix with the total values of the respective equations, 8 and 23. So we have negative 2, negative 3 in the first column, the coefficients of the x terms. And in the second column, we have 8 and 23, the total values of the equations. And now we can solve for dy by multiplying negative 2 times 23. And then we subtract the product of negative 3 times 8. And now we can solve for dy by multiplying negative 2 times 23, which is negative 46, minus negative 3 times 8 is negative 24. Negative 46 minus negative 24 is negative 46 plus 24. And negative 46 plus 24 shows us that dy is equal to negative 22. So now that we know d, dx, and dy, we can find the solution. So we first want to divide dx by d to find x. So let's move equations a and b to the side for a moment and just work with our determinants. And when we divide 55 by negative 11, this will give us x. 55 divided by negative 11 is negative 5. So we see x is equal to negative 5. And now for the y, we want to divide dy, which is negative 22, by d, which is negative 11. So y is equal to negative 22 divided by negative 11, which is positive 2. So we see that the solution to this 2 by 2 system is the point where x is negative 5 and y is positive 2. And now we can check the answer by plugging the xy, negative 5 and 2, into the original equations. That would give us negative 2 times negative 5, which is 10. 10 minus 2 is equal to 8, leaving us with the true statement 8 is equal to 8, confirming these are the correct values for x and y. And now for equation b, we would get negative 3 times negative 5, which is 15, plus 4 times 2, which is 8. 15 plus 8 is equal to 23, giving us the true statement 23 is equal to 23. So we see the solution to question number 2 is the point where x is negative 5 and y is 2. Let's now have a look at question number 3. Step 1, create a coefficient matrix. So the first column will have the coefficients of our x terms, 2 and negative 3. The second column will have the coefficients of the y terms, 4 and positive 1. And now that we have our 2 by 2 coefficient matrix, we can solve for d. So we want to multiply 2 times 1, and then subtract the product of negative 3 times 4. So we see d is equal to 2 times 1, which is 2, minus negative 3 times 4, which is negative 12. 2 minus negative 12 is equivalent to 2 plus 12, and that's equal to 14. So we see d is equal to 14. So we put that to the side, and now we want to find dx. So we replace the first column of the coefficient matrix with the values of the respective equations. So this is the 2 by 2 matrix we'll use to solve for dx. So we multiply negative 2 times 1, and then subtract the product of negative 11 times 4, giving us negative 2 times 1, which is negative 2, minus negative 11 times 4, which is negative 44. Negative 2 minus negative 44 is equivalent to negative 2 plus 44. And negative 2 plus 44 shows us that dx is equal to 42. So we can now put dx to the side for a moment so that we can focus on finding dy. So you want to replace the second column of the coefficient matrix with the values of the respective equations. So the 2 by 2 that we get, the first column is 2, negative 3, the coefficients of the x terms. And the second column is negative 2, negative 11, the values of the equations. And now we can solve for dy. So we first multiply 2 times negative 11. And then we subtract the product of negative 3 times negative 2. So 2 times negative 11 is negative 22, minus negative 3 times negative 2, which would be 6. Negative 22 minus 6 is equal to negative 28. So we see dy is equal to negative 28. So now we've found all three determinants, d, dx, and dy. So we can use these three determinants to solve for x and y. So we'll first solve for x by dividing dx, which is 42, by d, which is 14. So let's move these two equations to the side for a moment and just work with our three determinants. So to solve for x, we divide 42 by 14, showing us x is equal to positive 3. And now step 9, divide dy by d, and this will give us the y coordinate. So y is equal to negative 28 divided by 14, which shows us that y is equal to negative 2. So now that we've found the x and the y, we see that the solution to this 2 by 2 system is the point where x is 3 and y is negative 2. In step 11, we can check the answer by plugging the xy into the original equations. When we do so, equation A, we get 2 times 3, which is 6, plus 4 times negative 2, which is negative 8. 6 minus 8 is negative 2, giving us the true statement, negative 2 is equal to negative 2, confirming that these are the correct values for x and y for equation A. And now equation B, we have negative 3 times 3, which is negative 9, minus 2. Negative 9 minus 2 is equal to negative 11, giving us another true statement, negative 11 is equal to negative 11, confirming that x is 3 and y is negative 2 is the solution to question number 3. So that is how you use Cramer's rule to solve 2 by 2 systems. Let's now discuss how we go about calculating the determinant of a 3 by 3 system. And to do so, we'll review two different methods. So we'll take a look at those methods separately. A 2 by 2 system has two equations with two unknown variables. For 3 by 3s, we have three equations, A, B, and C, that have three variables, x, y, and z. So the matrix that we'll be working with to calculate the determinants are 3 by 3. The first column represents the coefficients of our x terms, 1, negative 1, and 2. The second column represents the coefficients of our y terms, positive 1, negative 2, and positive 2. And the third column is represented by the coefficients of these z terms, positive 1, positive 2, and negative 1. So the 3 by 3s we'll be working with represent the coefficients of our three variables. But let's now walk through an example together to take a look at method number 1, So find the determinant of this 3 by 3. Column 1 is 1, -1, and 2. Column 2 is 1, -2, and 2. And column 3 is 1, 2, -1. Now, calculating the determinant of a 3 by 3 is slightly different than calculating a 2 by 2. We'll still be multiplying the numbers going down to the right and up to the right. But before we do that, the first step is to rewrite the first 2 columns to the right of the matrix. So we take column number 1 and column number 2, and we rewrite both to the right of the 3 by 3. So on the outside of our vertical line. So now we have a total of 5 columns, 1, 2, 3, 4, 5. We still have 3 rows, 1, 2, and 3. But now with this new setup, we can now multiply the numbers going down to the right, starting with row 1, column 1, row 1, column 2, and row 1, column 3. So when we multiply going down to the right, starting with row 1, column 1, we multiply +1 times -2 times -1. And what we're going to do is we're going to add the products from this step. So we multiply these numbers, put a positive in front of it. Since it's positive, we can just leave it as is. And now we'll go to R1C2. So still the first row, the next column over. And again, we want to multiply the numbers going down to the right. And we want to add this product. So we'll place a positive sign. And then we'll multiply 1 times 2 times 2. And then we repeat this process one more time, starting at R1C3. So we stay in the first row, but now we move over to the third column. And again, we multiply going down to the right. So each time we're going down to the right, we go down 1 row and over 1 column. This time we have 1 times -1 times 2. And for all 3 of these, they're all preceded with a positive sign. So those are step 2 and step 3. Now, step 4 and step 5, we first want to multiply the numbers going up to the right, starting with row 3, column 1, row 3, column 2, and row 3, column 3. So this time we're moving up, and this time we're starting, instead of with row 1, we're starting with row 3. And now when we multiply these numbers, instead of adding these products, we're going to subtract them. So we'll place a negative or minus sign in front of each product. So starting with row 3, column 1, row 1, row 2, row 3. Column 1 is furthest to the left, so we're starting with +2. And now we multiply the numbers going up to the right. So that gives us 2 times -2 times 1 here. And we place a minus sign in front of it since we are subtracting the products that we get when we're going up. So now we multiply the numbers starting with R3, C2, which should be +2 here. And when we multiply going up to the right, go up 1 row, go over 1 column for each one. We get 2 times 2 times 1. And we place a minus or negative sign in front of it. And now we multiply the numbers going up to the right, starting with row 3, column 3. So the third row, third column, so that would be -1. Going up to the right means we're multiplying -1 times -1 times 1. And we want to place a minus sign in front of it. So now, step 6, we can solve for D by evaluating this expression. So let's move the matrix to the side for a moment and evaluate each piece. So first we have 1 times -2 times -1, which would be equal to -2 times -1, which is +2. Then we add that to 1 times 2, which is 2, times 2, which would be 4. And then we add that to the product of 1 times -1, which is -1. Negative 1 times 2 is negative 2. And then we have minus 2 times negative 2 times 1. Negative 1 times 2 is negative 2. Negative 2 times negative 2 is positive 4. And positive 4 times 1 is positive 4. Then we have minus 2, which would be negative 2, times 2, which is negative 4, times 1, which is negative 4, minus negative 1. Negative 1 times negative 1 is positive 1. Positive 1 times negative 1 is negative 1. And negative 1 times positive 1 is negative 1. So D will be equal to 2 plus 4, which is 6. 6 minus 2 is 4. 4 plus 4 is 8. 8 minus 4 is 4. And 4 minus 1 is equal to 3. So the determinant of the system is equal to 3. So that is how we go about finding the determinant of a 3x3 system using method number 1. Let's now have you try a few practice questions. Question number 1, find the determinant of this 3x3. Column 1 is 1, negative 2, positive 2. Column 2 is negative 1, positive 1, positive 3. And the third column is 2, negative 1, negative 2. Question number 2, column 1 is 1, negative 1, and positive 3. The second column is negative 1, 2, negative 3. And the third column is negative 1, negative 2, and positive 1. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1, rewrite the first two columns to the right of the matrix. So we take columns 1 and 2, and we rewrite both to the right of our third column. So we place them here. And now step 2, multiply the numbers going down to the right, starting with R1, C1. And then we want to add the products. So we have 1 times negative 2. It's positive in front. And now we go to R1, C2. So that would be first row, second column, negative 1. And we multiply the numbers going down to the right, giving us negative 1 times negative 1 times 2. And we're going to place a positive sign in front of that product. And now we go to R1, C3. So the first row, third column is positive 2 here. And we multiply the numbers going down to the right, giving us 2 times negative 2 times 3. And we're going to place a positive sign in front of it. So those are steps 2 and 3. Step 4, multiply the numbers going up to the right, starting with R3C1. So that would be the third row, first column, which is positive 2. And then we're going to subtract the products from this step. So if we're multiplying going up to the right, we have 2 times 1 times 2. And we're going to place a minus sign in front of it since we are subtracting these products. And now we go to R3C2, third row, second column, so that's positive 3 here. And we want to multiply the numbers going up to the right, which would be 3 times negative 1 times 1. And we'll place a minus sign in front of it since we're subtracting it. And now, starting with R3C3, third row, third column, is negative 2 here. And we multiply the numbers going up to the right, which would be negative 2 times negative 2 times negative 1. And we'll place a minus sign in front of that product. So now step 6, we can solve for d by evaluating this expression. So let's put the matrix to the side. And we see d is equal to 1 times 1, which is 1. 1 times negative 2 is negative 2. Plus negative 1 times negative 1, which is positive 1. Positive 1 times 2 is positive 2. Plus 2 times negative 2, which is negative 4. Negative 4 times 3 is negative 12. Minus 2 times 1, which would be negative 2 times 1, which is negative 2. Negative 2 times 2 is negative 4. Minus 3, which would be negative 3, times negative 1, which would be negative 3 times negative 1, which is positive 3. And positive 3 times positive 1 is positive 3. Negative 1 times negative 2 is positive 2. Positive 2 times negative 2 is negative 4. And negative 4 times negative 1 is positive 4. So we see d is equal to negative 2 plus 2, which would be 0. 0 minus 12 is negative 12. Negative 12 minus 4 is negative 16. Negative 16 plus 3 is negative 13. And negative 13 plus 4 is negative 9. So the answer to question number 1 is d is equal to negative 9. So that is the answer to question number 1. Let's now have a look at question number 2. Step 1, rewrite the first 2 columns to the right of the matrix. So we have column 1 and column 2, and we want to rewrite both of these here to the right of the matrix that we were given. And now, step 2, multiply the numbers going down to the right, starting with R1, C1, which would be positive 1 here. And step 3, add the products from step 2. So we'll place a positive sign in front of each one, giving us 1 times 2 times 1, plus negative 1 times negative 2 times 3, plus negative 1 times negative 1 times negative 3. So those are steps 2 and 3. So now step 4, multiply the numbers going up to the right, starting with R3, C1, R3, C2, and R3, C3. And then step 5, subtract the products from step 4. So we'll place a minus sign in front of each of these products, giving us minus 3 times 2 times negative 1, minus negative 3 times negative 2 times 1, minus 1 times negative 1 times negative 1. And now, step 6, we can solve for d by evaluating this expression. So let's move our matrix to the side. And we see d is equal to 1 times 2, which is 2. 2 times 1 is 2. Plus negative 1 times negative 2 is positive 2. Positive 2 times 3 is positive 6. Plus negative 1 times negative 1 is positive 1. Positive 1 times negative 3 is negative 3. Minus 3, so that's negative 1 times 3, which is negative 3, times 2 would give us negative 6. And negative 6 times negative 1 is positive 6. Then we have negative 1 times negative 3 is positive 3. Positive 3 times negative 2 is negative 6. And negative 6 times positive 1 is negative 6. And negative 1 times 1 is negative 1. Negative 1 times negative 1 is positive 1. And positive 1 times negative 1 is negative 1. So we get d is equal to 2 plus 6, which is 8, minus 3 would be 5. 5 plus 6 is 11. 11 minus 6 is 5. And 5 minus 1 would be 4. So the answer to question number 2 is D is equal to 4. So that is how we go about calculating the determinant of a 3x3 using this method. Let's now move on to discuss a second method. A quick reminder, the method we just reviewed, method number 1, the first method of calculating the determinant of a 3x3 system works for 3x3 systems, but not systems that are 4x4 or higher. So the method we just saw, we start with a 3x3, and then we rewrite columns 1 and 2 to the right of it. And from here, we multiply the numbers going down to the right and add those products. And then we multiply the numbers going up to the right and subtract those products. And this is the process we use for Cramer's rule for the first method to find the determinant. But since we cannot use this method for anything but 3x3s, we want to have a second method that we can use for both 3x3 systems and systems that are 4x4 or higher. So you'll start with some 3x3 system, and you'll wind up working with 3 individual 2x2 matrices. And each matrix is preceded by a multiplier. Now we'll dive into the details of how we go from this 3x3 to these multipliers times these matrices. But a few things to review before we take a look at that process. Any row or column in the 3x3 can be used to create the resulting 2x2 systems. The multiplier of each 2x2 is the number in the 3x3 being used to create that 2x2. Now, something to keep in mind, the 2x2s that you get will vary based on the row or column that you choose to eliminate from the 3x3. So the 2x2s may be different, but the final determinants that you get will be the same, regardless of which row or column that you choose to eliminate from the 3x3. Now, I will always eliminate row number 1 just to make things easy. And what you want to do is, you first want to start with the first number in that row or column. This will be your multiplier. You draw a line through the remaining row and that same column. And the 2x2 is the resulting numbers that are not crossed out. So 5, 6, 8, 9 with a multiplier of 1. And now we have the next number in that same row, since I'm crossing out row number 1. So that would be 2, this multiplier here. Cross out the numbers in that same row and the same column. And the 2x2 are the numbers that are not crossed out, so 4, 7, 6, 9. And then we complete it by going to the last number in that row, 3. So that would be the multiplier here. Cross out the numbers in that row and in that column. And our new 2x2 is 4, 5, 7, 8. So that is how we wind up with these 3 2x2s. Now the sign in front of each 2x2 is determined by a sign box, like this one here. So we want to use a 3x3 sign box to choose the appropriate sign to place in front of each multiplier. So since we eliminated row 1, we want to use the signs in row 1. Positive 1 was in row 1, column 1. So since that's a positive sign, this would be positive 1. The multiplier 2 was in row 1, C2. So we put a negative in front of that 2. And the next sign is positive. So we place a positive in front of the 3. So since we chose to eliminate row 1, we use the signs from row 1. But if you use a column or a different row, you use the signs in that column or row. Again, for this chapter, I'm only going to use row 1 to keep things simple and consistent. That way it's easier to follow along. But let's go back to the beginning and work our way through an example. So you'll be asked to find the determinant of a 3x3. Column 1 is +1, -1, and +2. Column 2 is +1, -2, and +2. Column 3 is +1, +2, and -1. This is the same example that we used for method number 1. So you'll see that we will wind up getting this same determinant at the end. Step 1, circle the number in the first row in the first column. So the first row is furthest to the top. The first column is furthest to the left, so that would be here, +1. Now step 2, draw lines through the other numbers in the same row and column. So we draw a line through the remaining row and through that column. Now step 3, rewrite the number that is circled. So this would be our multiplier, 1. In step 4, create a 2x2 matrix with the numbers that are not crossed out. So that would be these 4 numbers here, giving us a row of -2, +2, and a second row of 2, -1. So now we have our 2x2 created with the first number in row 1. So now we want to work on a 2x2 for the next number in that row. So step 5, circle the number in the first row and second column. That would be +1 here. And then step 6, draw lines through the other numbers in the same row and column. So we cross out those numbers and then we draw a line straight down. So now we have -1, 2 in this column here and 2, -1 in this column here. So step 7, rewrite the number that is circled, +1. And then step 8, create a 2x2 matrix with the numbers that are not crossed out. So that'll create a row of -1, +2, and a second row of +2 and -1. So we have our second 2x2. So now we're ready to create our third 2x2. So we want to go to the next number in the same row. In step 9, circle the number in the first row and third column. So that's +1 here. In step 10, draw lines through the other numbers in the same row and column. So we'll use these 4 numbers to create our new 2x2. Step 11, rewrite the number that is circled. So this would be our multiplier for the third 2x2. And now step 12, create a 2x2 matrix with the numbers that are not crossed out. So that would give us a row of -1, -2. And a second row of 2, 2. So now we have 3 2x2s, each with a multiplier in front of it. So now we want to use a sign box to place the appropriate signs in front of each one. So step 13, place the appropriate sign in front of each multiplier. So we want to write out a 3x3 sign box, which we can create by starting with positive sign, switching to the negative, switching back to positive, switching back to negative, so on and so forth. So you alter between positive, negative, all the way through. And you select the row or column that you use to eliminate. So again, I'll be using row 1 each time. So the first multiplier should have a positive sign in front of it, so we can leave that. The second 2x2 should have a negative in front of it, so that's where this negative sign comes from. And the third 2x2 should have a positive sign in front of it, so that's where this positive comes from. And now step 14, we can solve for D. So let's put this sign box to the side. So you want to calculate the determinant of the 2x2 the way you normally would, and then multiply that times the multiplier. So starting with this 2x2 here, we have 1 times, we find the determinant, so it's -2 times -1, minus 2 times 2. And now we evaluate this expression. So starting inside, we have negative 2 times negative 1, which would be positive 2, minus 2 times 2, which would be 4. 2 minus 4 is negative 2. And 1 times negative 2 is negative 2. So our first 2 by 2 is equivalent to negative 2. And now we move on to the second one. So starting with the 2 by 2 matrix, we have negative 1 times negative 1 minus 2 times 2. And we're going to multiply this entire thing times negative 1. So now we can evaluate this starting inside the brackets, giving us negative 1 times negative 1, which is positive 1. Positive 1 minus 2 times 2 would be 4. So we get 1 minus 4. And 1 minus 4 would be negative 3. 1 times negative 3 is negative 3. Minus negative 3 is equivalent to plus 3. So now we know this 2 by 2 is equivalent to positive 3. And we can move on to the last 2 by 2 here. When we find the determinant of this matrix here, we get negative 1 times 2 minus 2 times negative 2. We're going to multiply this times positive 1. So starting inside of the brackets, we have negative 1 times 2, which is negative 2. Negative 2 minus 2 times negative 2 would be minus negative 4. Negative 2 minus negative 4 is the same as negative 2 plus 4. Negative 2 plus 4 is positive 2. And 1 times 2 is positive 2. So we see that the determinant is equal to negative 2 plus 3, which would be positive 1. And positive 1 plus 2 is equal to positive 3. So we get the determinant of the 3 by 3 system is equal to positive 3. So that is how you go about finding the determinant of a 3 by 3 system using method number 2. Let's now have you try a few practice questions. These are the same 3 by 3 matrices we had for method number 1. So you'll see that the solutions to these two questions are the same as the ones that we did for method number 1. So you'll see that both methods work. So find the determinant. Question number 1. Column 1, we have 1, negative 2, positive 2. Column number 2, we have negative 1, positive 1, and positive 3. In column number 3, we have 2, negative 1, and negative 2. Question number 2, column number 1, we have 1, negative 1, and 3. Column number 2, we have negative 1, positive 2, and negative 3. Column number 3, we have negative 1, negative 2, and positive 1. Pause the video, answer these questions, and then press play when you are ready to begin. Step 1, circle the number in the first row in the first column. So that would be this one right here. Step 2, draw lines through the other numbers in the same row and column. So we draw a line through the same row, and then we draw a line through the same column, leaving us with the 2 by 2 here. So step 3, rewrite the number that is circled. So that would be positive 1. And then step 4, create a 2 by 2 matrix with the numbers that are not crossed out, which would be these 4 here. So we wind up with a 2 by 2. Step 5, circle the number in the first row and the second column. So we'll move from positive 1 to negative 1. Circle negative 1. And then step 6, draw lines through the other numbers in the same row and column. So we draw a line through those and draw a line straight down, leaving us with these 4 numbers that are not crossed out. And now step 7, rewrite the number that is circled That would be -1. In step 8, create a 2x2 matrix with the numbers that are not crossed out. So that would give us this 2x2. And now we want to create a third 2x2. So step 9, circle the number in the first row in the third column. That would be +2. Step 10, draw lines through the other numbers in the same row and column. So we draw a line through these two numbers and draw a line through these two numbers, creating a new 2x2 with these 4 numbers here. Step 11, rewrite the number that is circled. That would be +2. In step 12, create a 2x2 matrix with the numbers that are not crossed out, which would be these 4 numbers here. So now we have 3 2x2 systems with multipliers in front of each one. So step 13, place the appropriate sign in front of each multiplier. So we can put this 3x3 to the side and create a sign box. And since we use the first row in our 3x3, we'll use the first row in this sign box for our signs. So the first multiplier should have a positive sign in front of it. So we can leave that as is, since that'll be the same. The second number in the row should have a negative sign placed in front of it. So that's where this negative comes from. And the third 2x2 should have a positive sign placed in front of it. That's where this comes from. And now we have all of the information we need to solve for D. So let's put the sign box to the side. And starting with the first 2x2, we have 1 times -2 minus 3 times -1. And we're multiplying this times +1. So starting inside of the brackets, we have 1 times -2, which would be -2, minus 3 times -1, which would be -3. -2 minus -3 is equivalent to -2 plus 3. -2 plus 3 is equal to +1. And 1 times 1 is equal to 1. So the first 2x2 gives us 1. The second 2x2, we get -2 times -2 minus 2 times -1. And we're going to multiply this times minus -1 on the outside. Starting on the inside, we have -2 times -2, which is +4. 4 minus 2 times -1 would be 4 minus -2, which is equivalent to 4 plus 2. And 4 plus 2 is 6. -1 times 6 is -6. 1 minus -6 is 1 plus 6. So for the second 2x2, we get 6. And now we can move on to the third 2x2, which is -2 times 3 minus 2 times 1. And we'll multiply this times +2. Starting inside of the brackets, we have -2 times 3, which is -6, minus 2 times 1, which is 2. -6 minus 2 is -8. 2 times -8 is -16. So now we see D is equal to 1 plus 6, which is 7. And 7 minus 16 is -9. So when we use method number 1, we found the determinant was equal to -9. And this time we use method number 2, and again the determinant is equal to -9. So that is the answer to question number 1. Let's now have a look at question number 2. Step 1, circle the number in the first row in the first column. So that would be this one here. And step 2, draw lines through the other numbers in the same row and column. Step 3, rewrite the number that is circled. So that would be +1. In step 4, create a 2x2 matrix with the numbers that are not crossed out. So that would be these 4 numbers here. and that gives us our first 2 by 2. We then move on to the next number in that row. So we go from +1 to -1. And now step 5, circle the number in the first row in the second column. And step 6, draw lines through the other numbers in the same row and column. So cross those out, cross these out. Step 7, rewrite the number that is circled. That would be -1. In step 8, create a 2 by 2 matrix with the numbers that are not crossed out. -1 and 3 from column 1, and -2, 1 from column 3. So this is the resulting 2 by 2. And now we can create a third one by step 9, circling the number in the first row in the third column. And then step 10, draw lines through the other numbers in the same row and column. Step 11, rewrite the number that is circled, -1. In step 12, create a 2 by 2 matrix with the numbers that are not crossed out. So that would be these 4 numbers here. So now we have our 3 2 by 2s. So step 13, place the appropriate sign in front of each multiplier. So we can move this matrix to the side and create a 3 by 3 sign box. And since we used row 1 to create our 2 by 2s, we want to use the signs in row 1. So our first 2 by 2 is preceded by a positive sign, so we can leave that as is. The second 2 by 2 is preceded by a negative sign, so we place that in front of -1. And the third sign is positive, so we place that in front of -1 here. And now we can move the sign box to the side and use this information to solve for D. So starting with the first 2 by 2, we have 2 times 1 minus -3 times -2. We're going to multiply this times +1. Starting with the inside of the brackets, we have 2 times 1, which is 2, minus -3 times -2 is 6. 2 minus 6 is -4. 1 times -4 is -4. So the first 2 by 2 gives us -4. The next 2 by 2, we have -1 times 1 minus 3 times -2. And we'll have minus -1 on the outside of that. Starting inside, we have -1 times 1, which is -1. -1 minus 3 times -2 is minus -6. Minus -6 is equivalent to +6. So we get -1 plus 6, which is 5. -1 times 5 is -5. Minus -5 is +5. And now our third 2 by 2, we have -1 times -3 minus 3 times 2. And we'll multiply this times plus -1 or -1. So starting inside, we have -1 times -3, which is +3, minus 3 times 2, which is 6. 3 minus 6 is -3. -1 times -3 is +3. So we see D is equal to -4 plus 5, which is +1. 1 plus 3 shows us that D is equal to +4. So we see that both methods work for calculating the determinant. Let's wrap up the chapter by reviewing how to solve 3 by 3 systems using Cramer's rule. And for this, we will only be using method number 1 for calculating determinants. Since we're working with 3 by 3s, the first method will work. So we'll use method number 1 for all of these questions. But if you use method number 2, you should still wind up with the same answers. So Cramer's rule is a process that uses 4 unique determinants, d, dx, dy, and dz, to find the solution, the xyz coordinate, of a 3 by 3 system. So we have a 3 by 3 and we'll use this to calculate d, dx, dy, and dz to help us find our solution. Now, let's discuss dx, dy, and dz a little bit further. The determinant dx is calculated by replacing the column with the coefficients of the x variable with the numbers that represent the total value of the equations. So when we're calculating the determinant of the system, we use a coefficient matrix. But when we want to calculate dx, we want to replace the column with the coefficients of the x variable and replace that with the total value of each equation. So we'll replace A in column 1 with D, we'll replace E in column 1 with H, and we'll replace I in column 1 with L. And now we'll use this 3 by 3 to find dx. dy and dz work similarly. The determinant dy is calculated by replacing the column with the coefficients of the y variable with the numbers that represent the total value of the equations. So for dy, the first column is the coefficient of the x variables, but the second column that normally would have the coefficients of the y variables are replaced by the total value of each equation. So we swapped out b and replaced it with d. We swapped out f and replaced it with h. And we swapped out j and replaced it with l. And now this is the 3 by 3 that we will use to find the determinant dy. And the last determinant that we need to find, dz, we can do so similarly. The determinant dz is calculated by replacing the column with the coefficients of the z variable with the numbers that represent the total value of the equations. So from our coefficient matrix, we replace c with d, we replace g with h, and we replace k with l. And now this is the 3 by 3 we would use to find dz. And once we go through this process and we find d, dx, dy, and dz, we can calculate the solution by dividing dx by d, by dividing dy by d, and by dividing dz by d. But there are some scenarios in which we'll realize that there are an infinite number of solutions for 3 by 3 or no solutions. So how do we know which scenarios those are? Well, if the determinant of the coefficient matrix is equal to 0, and the dx, the dy, and the dz determinants are all equal to 0, then the system is considered dependent and there are infinite solutions. So if d is equal to 0, and dx is equal to 0, and dy is equal to 0, and dz is equal to 0, if all four determinants are equal to 0, then that means we have a system with infinite solutions. But in the case where the determinant of the coefficient matrix is equal to 0, and the dx or the dy or the dz determinant is not equal to 0, then the system is considered inconsistent and there are no solutions. So for this one, we need d to equal 0, and then any of these three, either dx or dy or dz, if any of them are not equal to 0, so if dz is equal to 1, or if dy is equal to -1, or if dx is equal to 2, if any of these are not 0, then there are no solutions to the system. If they're all 0, infinite solutions. If one of them is not 0, then it's no solutions. And for both, d must be equal to 0. Okay, well, let's start at the beginning and walk through an example together. Use Cramer's rule to solve the system and then check the answer. Equation A, x plus y plus z is equal to 9. Equation B, -x plus 2y minus 2z is equal to -4. Equation C, 2x minus y plus 2z is equal to 9. So how would we solve this using Cramer's rule? Step 1, create a coefficient matrix. So we look at the coefficients for our x, y, and z terms and create a 3x3 matrix. So the first column, the coefficients of our x variables are 1, -1, and 2. So that's column 1. The second column, the coefficients of our y terms, +1, +2, and -1. So that's the second column. In our third column, the coefficients of our z terms are +1, -2, and +2. So that's our third column. And now, step 2, rewrite the first two columns to the right of the coefficient matrix. Remember, we're going to use the first method to calculate the determinants. So now we have the information we need to calculate d. So step 3, solve for d. Now we can move these equations to the side for a second, so we can use this to solve for d. So we'll start by multiplying the numbers going down to the right, beginning with row 1, column 1. So we have 1 times 2 times 2, and we add that to 1 times -2 times 2, and we add that to 1 times -1 times -1. Now we want to start with row 3, column 1, and multiply the numbers going up to the right and subtract these products. So we get -2 times 2 times 1, minus -1 times -2 times 1, minus 2 times -1 times 1. So now we can solve for d by evaluating this expression. So we get d is equal to 1 times 2 is 2, 2 times 2 is 4, plus 1 times -2, which is -2, and -2 times 2 is -4, plus 1 times -1, which is -1, and -1 times -1 is +1, minus 2, so that's -1 times 2, which is -2. -2 times 2 is -4, and -4 times 1 is -4. Then we have -1 times -1, which is +1. 1 times -2 is -2, and -2 times 1 is -2. -1 times 2 is -2. -2 times -1 is +2. And +2 times 1 is 2. So we get d is equal to 4 minus 4, which is 0, plus 1 is 1, minus 4 is -3, minus 2 is -5, plus 2 would give us -3. So we get d is equal to -3. So we can put that to the side. And now we want to try to find dx. So we want to go back to our three equations. And now, step 4, replace the first column of the coefficient matrix with the values of the respective equations. So we swapped out the coefficient +1 and replaced it with 9 here. In the second row, we swapped out -1 and replaced it with -4 here. And in row 3, we replaced +2 with +9 here. And now that we have our 3x3 to find dx, step 5, rewrite the first two columns to the right of the coefficient matrix. And now we have what we need to solve for dx. So we multiply, starting with row 1, column 1, the numbers going down to the right. And we repeat this process for column 2 going down to the right, and column 3 going down to the right. And we add these products together. So that gives us 9 times 2 times 2, plus 1 times -2 times 9, plus 1 times -4 times -1. And now we go to row 3, column 1, and we multiply the numbers going up to the right, and we subtract these products and we repeat this for column 2 and column 3. So starting with 9, we get minus 9 times 2 times 1, minus negative 1 times negative 2 times 9, minus 2 times negative 4 times 1. And now we have the expression we need to find dx. So we get 9 times 2, which is 18, times 2, which is 36, plus 1 times negative 2, which is negative 2, times 9 is negative 18, plus 1 times negative 4 is negative 4, times negative 1 is positive 4. Negative 1 times 9 is negative 9. Negative 9 times 2 is negative 18. Times 1 is negative 18. Negative 1 times negative 1 is positive 1. Positive 1 times negative 2 is negative 2. And negative 2 times 9 is negative 18. And finally, negative 1 times 2 is negative 2. Times negative 4 is positive 8. Times 1 is positive 8. So dx is equal to 36 minus 18, which is 18, plus 4 is 22. 22 minus 18 is 4. 4 minus 18 is negative 14. And negative 14 plus 8 is equal to negative 6. So we find that dx is equal to negative 6. And now we can put that to the side and focus on finding dy. So we want to go back to our 3 equations. In step 7, replace the second column of the coefficient matrix with the values of the respective equations. So we go to the second column where we normally find the coefficients of our y terms and replace these coefficients with 9, negative 4, and 9. And now step 8, rewrite the first 2 columns to the right of the coefficient matrix. So once we complete these 2 steps, we are ready to solve for dy. So we first want to multiply the numbers going down to the right, starting with row 1, column 1, which is positive 1. And we'll repeat this for column 2 and column 3, and we'll add these products together. So we get 1 times negative 4 times 2, plus 9 times negative 2 times 2, plus 1 times negative 1 times 9. And now we want to start here with 2 and multiply the numbers going up to the right. And we'll repeat this for columns 2 and 3. And we'll subtract all of these products. So we get minus 2 times negative 4 times 1, minus 9 times negative 2 times 1, minus 2 times negative 1 times 9. And now we have the expression that we need to solve for dy. So we have 1 times negative 4, which is negative 4, times 2 is negative 8, plus 9 times 2, which is negative 18, times 2 is negative 36, plus 1 times negative 1, which is negative 1, times 9 is negative 9. Negative 1 times 2 is negative 2, times negative 4 is positive 8, times 1 is positive 8. Negative 1 times 9 is negative 9, times negative 2 is positive 18, times 1 is positive 18. And negative 1 times 2 is negative 2, times negative 1 is positive 2, times 9 is 18. So we see that dy is equal to negative 8 minus 36 minus 9 plus 8 plus 18 plus 18, which will equal negative 9. And now that we've found dy, we want to go back to the original 3 equations so that we can create a coefficient matrix, but we want to replace the third column of the coefficient matrix with the values of the respective equations. So our third column, instead of it being 1, -2, and 2, it is instead 9, -4, and 9. And step 11, rewrite the first two columns to the right of the coefficient matrix. And once this is complete, we are ready to solve for dz. So we get 1 times 2 times 9 plus 1 times -4 times 2 plus 9 times -1 times -1. And now we start row 3, column 1 here, and multiply the numbers going up to the right, and subtract the product that we get when we do this here, here, and here. So we get minus 2 times 2 times 9, minus -1 times -4 times 1, minus 9 times -1 times 1. And now we have the expression that we need to solve for dz. So we get dz is equal to 1 times 2, which is 2, times 9, which is positive 18, plus 1 times -4, which is -4, times 2 is -8, plus 9 times -1, which is -9, times -1 is positive 9. -1 times 2 is -2, times 2 is -4, times 9 is -36. -1 times -1 is positive 1. Positive 1 times -4 is -4. Times 1 is -4. -1 times 9 is -9. Times -1 is positive 9. Times 1 is positive 9. So we see dz is equal to 18 minus 8, which is 10, plus 9 is 19. 19 minus 36 is -17. -17 minus 4 is -21. And -21 plus 9 shows us that dz is equal to -12. So now we have found d, dx, dy, and dz. So we can now find x, y, and z. So first, divide dx by d, and then solve for x. So that would be -6 divided by -3. And that shows us that x is equal to positive 2. So that's our x value. Now let's find y. So we want to divide dy by d. So that shows us that y is equal to -9 divided by -3, which means y is equal to positive 3. And for z, we want to divide dz by d. So that shows us that z is equal to -12 divided by -3, which would be positive 4. So the solution to the system is the point where x is 2, y is 3, and z is 4. And you can check the answer by plugging the x, y, z, 2, 3, 4 into the original equations to make sure all three statements are true when we plug in these values for x, y, and z. So for equation A, we get 2 plus 3, which is 5, plus 4, which is 9. 9 is equal to 9 confirms that these are the correct values for x, y, and z. So now we look at equation B, and we get -2 plus 2 times 3, which is 6, minus 2 times 4, which is -8. -2 plus 6 is positive 4, and positive 4 minus 8 is -4. -4 is equal to -4 confirms these are the correct values for x, y, and z for equation B as well. And for equation C, we get 2 times 2, which is 4, minus 3, plus 2 times 4, which is 8. 4 minus 3 is 1, and 1 plus 8 is 9, giving us 9 is equal to 9, confirming that x is equal to 2, y is equal to 3, and z is equal to 4. is the solution to this system. So that is how you would go about using Cramer's rule to solve a 3x3 system. Let's wrap up the chapter by having you complete a few practice questions. Use Cramer's rule to solve the system and then check the answer. Question number 1, equation A, x plus y plus z is equal to -2. Equation B, x minus 2y minus 2z is equal to 16. Equation C, 3x minus y plus 2z is equal to 9. Question number 2, equation A, x minus y plus z is equal to -6. Equation B, -x plus 2y minus z is equal to 11. And equation C, 2x minus 3y plus 2z is equal to -17. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1. Step 1, create a coefficient matrix. So we'll use the coefficients for x, y, and z to create a 3x3. So column 1, the coefficients of our x terms, 1, 1, and 3. The second column, the coefficients of our y terms, 1, -2, and -1. And the third column, the coefficients of our z terms, +1, -2, and 2. So this is our coefficient matrix. And now step 2, rewrite the first 2 columns to the right of the coefficient matrix. So we rewrite these 2 columns here. And now we have what we need to solve for D. So starting with row 1, column 1, we're going to multiply 1 times -2 times 2 and add that to 1 times -2 times 3, and then add that to 1 times 1 times -1. And now we want to go down to row 3 and multiply the numbers going up and subtract those products. So we get -3 times -2 times 1 minus -1 times -2 times 1 minus 2 times 1 times 1. And now we have the expression that we need to solve for D. So we get D is equal to 1 times -2, which is -2, times 2, which is -4, plus 1 times -2, which is -2, times 3 will give us -6, plus 1 times 1, which is 1, times -1 is -1. And we have -1 times 3 is -3, times -2 is +6, times 1 is +6. -1 times -1 is +1, times -2 is -2, times 1 is -2. -1 times 2 is -2, times 1 is -2, times 1 is -2. So we see D is equal to -4 minus 6, which is -10, minus 1 is -11, plus 6 is -5, minus 2 is -7, and minus 2 is -9. So we get D is equal to -9. We now put that to the side so that we can try to find dx. So we'll go back to our 3 equations. And step 4, replace the first column of the coefficient matrix with the values of the respective equations. So we remove the coefficients of the x terms and replace +1 with -2 in the first row. Replace +1 with 16 in the second row. And replace +3 with positive 9 in the third row. And now we want to rewrite the first two columns to the right of the coefficient matrix. And now we have what we need to solve for dx. So we have negative 2 times negative 2 times 2 plus 1 times negative 2 times 9 plus 1 times 16 times negative 1 minus 9 times negative 2 times 1 minus negative 1 times negative 2 times negative 2 minus 2 times 16 times 1. So once we do this, we have the expression we need to solve for dx. So we get dx is equal to negative 2 times negative 2, which is 4, times 2 will give us 8, plus 1 times negative 2, which is negative 2, times 9 is negative 18, plus 1 times 16, which is 16, times negative 1 is negative 16. Negative 1 times 9 is negative 9, times negative 2 is positive 18, plus 1 is positive 18. Negative 1 times negative 1 is positive 1, times negative 2 is negative 2. Negative 2 times negative 2 is positive 4. And negative 1 times 2 is negative 2, times 16 is negative 32, times 1 is negative 32. So we see dx is equal to 8 minus 18, which is negative 10. Negative 10 minus 16 is negative 26. Negative 26 plus 18 is negative 8. Negative 8 plus 4 is negative 4. And negative 4 minus 32 is negative 36. So we find that dx is equal to negative 36. And now we can put this to the side so that we can try to find dy. So we can go back to our three equations and replace the second column of the coefficient matrix with the values of the respective equations. So in row 1, we replace positive 1 with negative 2. In the second row, we replace negative 2 with 16. And in the third row, we replace negative 1 with 9. And now step 8, rewrite the first two columns to the right of the coefficient matrix. So now we can solve for dy. So we can put those to the side and work with just this. So we get 1 times 16 times 2 plus negative 2 times negative 2 times 3 plus 1 times 1 times 9. And then we do minus 3 times 16 times 1 minus 9 times negative 2 times 1 minus 2 times 1 times negative 2. Once we do this, we now have the expression we need to solve for dy. So we get 1 times 16 is 16, times 2 is 32, plus negative 2 times negative 2 is 4, times 3 is positive 12, plus 1 times 1, which is 1, times 9 is 9. Then we have negative 1 times 3 is negative 3, times 16 is negative 48, times 1 is negative 48. Negative 1 times 9 is negative 9, times negative 2 is positive 18, times 1 is positive 18. Negative 1 times 2 is negative 2, times 1 is negative 2, times negative 2 is positive 4. So we see dy is equal to 32 plus 12, which is 44, plus 9, which is 53. 53 minus 48 is 5. 5 plus 18 is 23. And 23 plus 4 shows us that dy is equal to 27. So now that we found dy, we now want to try to find the last determinant dz. So we want to replace the third column of the coefficient matrix with the values of the respective equations. So instead of 1 negative 2 and positive 2 being the third column. It will instead be negative 2, 16, and 9. And now we want to rewrite the first two columns to the right of the coefficient matrix. And now we have what we need to solve for dz. So we get 1 times negative 2 times 9 plus 1 times 16 times 3 plus negative 2 times 1 times negative 1. And now we go to row 3, column 1, and multiply the numbers going up to the right and subtract these products. So we get minus 3 times negative 2 times negative 2 minus negative 1 times 16 times 1 minus 9 times 1 times 1. And now we have the expression that we need to solve for dz, giving us 1 times negative 2, which is negative 2, times 9 is negative 18, plus 1 times 16, which is 16, times 3 will give us positive 48, plus negative 2 times 1 is negative 2, times negative 1 is positive 2, negative 1 times 3 is negative 3, times negative 2 is positive 6, times negative 2 is negative 12, negative 1 times negative 1 is positive 1, times 16 is 16, times 1 is 16, negative 1 times 9 is negative 9, times 1 is negative 9, times 1 is negative 9. So dz is equal to negative 18 plus 48, which would be positive 30, plus 2 would be 32, minus 12 would give us 20, plus 16 would give us 36, minus 9 would give us 27. So now we have the values of all four determinants, d, dx, dy, and dz. So now we can find x, y, and z. So step 13, divide dx by d, and step 14, solve for x. So x is equal to negative 36 divided by negative 9, which shows us that x is equal to 4. In step 15, divide dy 27 by d, negative 9, showing us y is equal to 27 divided by negative 9, which is negative 3. In step 17, divide dz, which is 27, by d, which is negative 9, showing us z is equal to 27 divided by negative 9, which is negative 3. So the solution to our 3x3 system is the point where x is 4, y is negative 3, and z is negative 3. And the last step, check the answer by plugging the x, y, z, 4, negative 3, into the original equations. When we do so, we get 4 minus 3, which is 1, minus 3, which is negative 2, leaving us with a true statement, confirming these are the correct values for x, y, and z. For equation B, 4 minus 2 times negative 3, which is positive 6, minus 2 times negative 3, which is positive 6. 4 plus 6 is 10. 10 plus 6 is 16, giving us the true statement 16 is equal to 16, confirming these are the correct values for x, y, and z for equation B as well. In equation C, we get 3 times 4, which is 12, minus negative 3 is positive 3, plus 2 times negative 3 is negative 6. 12 plus 3 is 15. 15 minus 6 is 9. 9 is equal to 9, confirms that this is true as well. So we see the solution to question number 1 is the point where x is 4, y is negative 3, and z is negative 3. So that is the solution to question number 1. Let's have a look at question number 2. Step 1, create a coefficient matrix. So the first column, we have the coefficients of our x terms, 1, -1, and 2. The second column, we have the coefficients of our y terms, -1, 2, and -3. In the third column, we have the coefficients of our z terms, +1, -1, and +2. And now step 2, rewrite the first two columns to the right of the coefficient matrix. And now we have what we need to solve for D. So let's work with just this. So we start by multiplying the numbers going down to the right. So we get 1 times 2 times 2 plus -1 times -1 times 2 plus 1 times -1 times -3. And then we do minus 2 times 2 times 1 minus -3 times -1 times 1 minus 2 times -1 times -1. And now we have the expression that we need to solve for D, giving us 1 times 2, which is 2, times 2 is 4, plus -1 times -1 is 1, times 2 is 2, plus 1 times -1 is -1, times -3 is +3. -1 times 2 is -2. -2 times 2 is -4. -4 times 1 is -4. -1 times -3 is +3. +3 times -1 is -3. And -3 times 1 is -3. -1 times 2 is -2. -2 times -1 is +2. And +2 times -1 is -2. So we see D is equal to 4 plus 2, which is 6, plus 3, which is 9, minus 4 would be 5, minus 3 would give us 2, and 2 minus 2 would show us D is equal to 0. So we see this system, since D is equal to 0, this lets us know that this system either has an infinite number of solutions or it has no solutions at all. So if the remaining determinants all equal 0, then we have infinite solutions. But if we get one determinant that is not equal to 0, then we know that we have no solutions. So let's continue on and find dx. So we want to go back to our three equations and replace the first column of the coefficient matrix with the values of the respective equations. So we replace +1 with -6. We replace -1 with +11. And we replace +2 with -17. And we want to rewrite the first two columns to the right of the coefficient matrix and then solve for dx. So when we do so, we want to start here and we get -6 times 2 times 2 plus -1 times -1 times -17 plus 1 times 11 times -3. And then we go down to row 3 and we do minus -17 times 2 times 1 minus -3 times -1 times -6 minus 2 times 11 times -1. And now we have the expression that we need to solve for dx, giving us -6 times 2, which is -12. -12 times 2 is -24. Plus -1 times -1 is +1. Times -17 is -17. Plus 1 times 11, which is 11. Times -3 would give us -33. -1 times -17 is +17. Times 2 is 34. Times 1 is 34. -1 times -3 is +3. Times -1 is -3. Times -6 is +18. And -1 times 2 is -2. times 11 is negative 22, times negative 1 is positive 22. So we get dx is equal to negative 24 minus 17 minus 33 plus 34 plus 18 plus 22, which would be equal to 0. So now that we have found dx, we can put this value to the side, and now we want to try to find dy. So step 7, replace the second column of the coefficient matrix with the values of the respective equations. So we swap out negative 1 for negative 6. We swap out 2 for 11. And we swap out negative 3 for negative 17. And now we want to rewrite the first two columns to the right of the coefficient matrix and then solve for dy. When we do so, we get 1 times 11 times 2 plus negative 6 times negative 1 times 2 plus 1 times negative 1 times negative 17 minus 2 times 11 times 1 minus negative 17 times negative 1 times 1 minus 2 times negative 1 times negative 6. And now we have the expression that we need to find dy. So we get dy is equal to 1 times 11, which is 11, times 2 is 22, plus negative 6 times negative 1 is positive 6, times 2 is positive 12, plus 1 times negative 1, which is negative 1, and negative 1 times negative 17 is positive 17. Negative 1 times 2 is negative 2. Negative 2 times 11 is negative 22. Times 1 is negative 22. Negative 1 times negative 17 is positive 17. Positive 17 times negative 1 is negative 17. Times 1 is negative 17. Negative 1 times 2 is negative 2. Times negative 1 is positive 2. Times negative 6 is negative 12. So dy is equal to 22 plus 12 plus 17 minus 22 minus 17 minus 12. So dy is equal to 0. So now we can put this value to the side so we can try to find dz now. So step 10, replace the third column of the coefficient matrix with the values of the respective equations. So we swap out positive 1 for negative 6. We swap out negative 1 for positive 11. And we swap out positive 2 with negative 17. And now we want to rewrite the first two columns to the right of the coefficient matrix. And with this information now, we can solve for dz. So when we do so, we get 1 times 2 times negative 17 plus negative 1 times 11 times 2 plus negative 6 times negative 1 times negative 3 minus 2 times 2 times negative 6 minus negative 3 times 11 times 1 minus negative 17 times negative 1 times negative 1. And with this, we now have what we need to find dz, giving us dz is equal to 1 times 2, which is 2, times negative 17 is negative 34, plus negative 1 times 11 is negative 11, times 2 is negative 22, plus negative 6 times negative 1 is positive 6, times negative 3 is negative 18, negative 1 times 2 is negative 2, times 2 is negative 4, times negative 6 is positive 24, negative 1 times negative 3 is positive 3, times 11 is 33, times 1 is 33. Negative 1 times negative 17 is 17, times negative 1 is negative 17, times negative 1 is positive 17. So we get dz is equal to negative 34 minus 22 minus 18 plus 24 plus 33 plus 17. So we see dz is equal to 0. And with this, we find that each of our determinants is equal to 0, all 4 of them. So when this happens, that lets us know there are infinite solutions. So for our 3x3 system, we found that there are infinite solutions for question number 2. And that concludes this chapter on Cramer's rule. Should you have any follow-up questions, feel free to leave them in the comments section. Or you can contact a tutor in your neighborhood by visiting bookandtable.com or by downloading our app on the App Store. Peace.